So, good afternoon, ladies and gentlemen. Today's speaker is Zeman from Charles University. Now, so Jirka finished his master's in 2019. He was a student here, and then he went for a PhD to the University of Augsburg, and his advisor was Professor Ben Schmidt. And now he is back in the group of Christoph Allolio here at the faculty in the Mathematical Institute of the Charles University. And I think his research altogether could be labeled like variational methods in material science. And from this box he will talk also today. His topic is Bending-torsion theorems for elastic and brittle nanowires.
Thank you very much, Martina, for the introduction. I was really a master's student of Martin Kružík here. I'm grateful to him for inviting me here and also for showing the very interesting field of nonlinear elasticity to me, which also inspired me to pursue my PhD studies in Augsburg, Germany. You can see the building of Mathematical Institute here near a lake, the other research staff, and my PhD advisor, Ben Schmidt, that you will be able to hear at this seminar on 11th December. In my PhD project, we drew inspiration from three paths of research in applied analysis, and that is rigorous derivation of elasticity theories for plates, rods, and so on, so-called dimensional reduction. Then from discrete to continuum limits, where you start with an atomistic description and derive some continuum model, and from fracture mechanics. And we did this to be able to describe some one-dimensional nanostructures. So probably it might be beneficial to catch a glimpse of nanotechnology. So, and now I will play a small video. You will see a carbon nanotube that is bent by a micro manipulator, and also the length scale is shown 200 nanometers. And I'm showing the video so that you can see that the nanotube really deforms a lot. It's beyond the range of linear elasticity, and this also demonstrates that the mechanical response of nano objects can be very different from bulk materials. Now we can go back to the presentation. And these objects have various names since the 90s, when the first boom of interest in carbon nanotubes started. Many kinds of 1D nanostructures have been synthesized. And in this word cloud, the size of a word approximately corresponds to the number of entries you receive on a Google Scholar. So nanowires are one of the most researched 1D nano objects. Not all of them are the same, but sometimes the nomenclature is not yet fixed. In particular, we were interested in semiconductor and ceramic nanowires that can be made of materials such as zinc oxide or the other ones that you see here. And mechanically, they can deform in the regime of large deflections, but also fracture can occur. They have promising applications in electronic devices, but some of them also in medicine, like titanium dioxide. And in the modeling, some challenges that people face are that the response depends on their structure or the diameter. So the traditional theories do not apply so well. Also, surface effects can't be neglected on this scale. Now let's go through some background on these three branches of applied analysis a bit. This is some basics of Kirchhoff's rod theory. It models the bending and torsion of some thin curve, let's say, moving in the three-dimensional space, and extension or transverse shear are neglected. And then if you take an isotropic linearly elastic constitutive assumption, you can formulate the static problem in a variational way, and it's formally equivalent to the balance of angular momentum of the rod. And to be able to describe torsion and bending, there's not only the tangent vector to the rod, but also two directors, which form an orthonormal frame that moves along the rod, and this gives you a richer model. Of course, many such theories have been derived, as Mora and Müller put it. There's a great variety, but the theories are often not consistent with each other. So it's important to be able to determine the range of validity of different theories. And probably at this seminar, I don't need to convince anyone that these theories are still used and important. Among the all the approaches that can be used to derive such dimensionally reduced theories, I think that gamma convergence kind of stands out, because we don't need to assume a particular ansatz on the solution of the equations of three-dimensional elasticity, and also it provides sufficient mathematical rigor that can be then used even in numerical mathematics or neighboring fields. A big success was the paper of Frieseke, James, and Miller, where they derived a quantitative rigidity estimate by which they rigorously derived the Kirchhoff nonlinear plate bending theory using gamma convergence, and also by this they clarified what coefficient should be present in the stored energy functional, and that really the lateral the lateral contraction of the plate shouldn't be neglected, but you only obtain this when you do it rigorously. And then there was another paper with the dimension reduction from 3D to 1D that derived a nonlinear Bending-torsion theory, where Kirchhoff rods that you saw on one of the previous slides is a special case. Then when we shift to discrete to continuum limits, John Ball listed this among open problems in elasticity in his review paper from 2002. It's convenient to work with the stored energy density of an elastic deformation, but where can we take an expression for it, or can it be derived from some microscopic quantities? That's the question. And then different researchers pursued different paths. One prominent problem is the Cauchy-Born rule, where you want to see if under the prescription of affine boundary conditions, the atoms also follow this affine map, or if they relax in a different way. If they do, it means that a simple continuum theory cannot be applied. Then some works considered points-twice limits of the interaction energies, and these three authors not only provide results for molecular dynamics as a starting point, that is some interaction potentials, but they can also start with some traditional model of electronic structure, the Thomas Fermi theory. Then there are some papers taking gamma limits, some of them also involving my advisor, Ben Schmidt. And another problem could be that if we are given some solution of the equations of elasticity, then is there some atomistic deformation in the neighborhood? I can't list all the papers, but here are two more recent ones, and then there is also a nice survey from 2007. Now, the interest of mathematicians in fracture mechanics or brittle fracture mechanics was renewed in 1998 when Franfort and Marigot revisited Griffith's energetic criterion, and since then there have been many papers involving some elastic fracture functionals where you have the stored elastic energy, but also some kind of fracture term where K is the toughness, and the integration is taken over some discontinuity set of the deformation. And since the physical world is very rich and interesting, obviously there have been efforts to unite some of these paths. So if we consider dimension reduction with discrete to continuum limits at the same time, it can give you some models for thin films or nanotubes. In particular, if you take the so-called ultra-thin scaling, that is when the interatomic distance is of the same order as the thickness of the structure, this can give you some new models for plates, thin films, or von Karman plates, or rods, as you will see in the sequel. Atomistic effects lie at the core of crack formation and propagation, but curiously, only specific situations are explored up to now, like 1D chains of atoms, sometimes at non-zero temperature, then scalar valued models, or the regime of membranes studying cleavage in some crystal lattice. And when it comes to dimension reduction with fracture, there have been many papers around the year 2020 in linearized elasticity, but in large deformations, there are still things to do. Well, even in the linearized setting. Some of the works feature Stefano Almi that you will be able to hear at this seminar at the end of November. And what's probably the most interesting is that the dimension reduction for Kirchhoff plates with fracture is an open problem, at least when I checked a few months ago. I still couldn't see any work solving this. Ben-Schmidt performed the reduction from 2D to 1D, but it relies on some quantitative piecewise rigidity estimate in SBD that they derived with Manuel Friedrich, but unfortunately this is only available in 2 dimensions. Now, in a nutshell, we derive continuum theories for the bending, twisting, and brittle fracture of rods in 3-dimensional space, whose cross-section may contain only a few atoms. We do this by sending the interatomic distance and thickness simultaneously to 0. Now let me describe the discrete model that we start from, and also the effective theories in pure elasticity, that is, without fracture. Imagine a thin rod with length L and a cross-section S epsilon H, and we can inscribe into this continuum domain a lattice lambda epsilon. Then we take sequences of interatomic distances and thicknesses tending to 0. And I will explain later what limiting regimes we can consider. Y epsilon are some atomistic deformations, and we will also need this cross-sectional lattice. We are restricted to cross-sections that are unions of full squares because hanging atoms can be troublemakers in compactness. But the cross-section doesn't need to be simply connected. Now let me clarify the dependence of thickness on the interatomic distance. If the thickness is still much larger than the interatomic distance, then these zigzag cross-sections finally exploit continuum 2-dimensional cross-section S, and we speak of thin rods. And in ultra-thin rods, these 2 quantities are of the same order, so we have a fixed cross-section for every epsilon, or the same shape. And now we need some way how to describe strain. So since we are on a cubic lattice, there can be 8 displacements that we kind of need to keep track of. So in this 3×8 matrix, each column corresponds to the displacement of one corner of this elementary cube. And then this forms a so-called discrete gradient. Then it is convenient to work with cell energy functions, because like this, it's possible to transform these sums into integrals and then use conversions in Sobolev spaces and all the machinery. But here is an example showing that this actually covers important cases from applications. Here we can see pair interaction potentials of nearest neighbors and next to nearest neighbors in the atomic lattice. And like this, it's possible to define a cell energy function in this way when you somehow put each bond partly into the neighboring cells. In the assumptions on the cell energy, we have frame indifference. Then the cell energy is minimized on rigid deformations, and these are the only minimizers. And to be able to use Taylor's expansion, we assume smoothness in the neighborhood of some discrete set of rotations, and quadratic growth, although this can be relaxed partly for, in a way, very thin rods. Cell energies have been used previously by Isaac and Tyle in 2004 or later in the authors listed there. Then we scale the energies. This power of the thickness corresponds to the bending and torsion regime, and it's also multiplied by this discrete volume element to have a finite energy per volume. And we interpolate the deformations in a piecewise finer manner that is also useful for the analysis, that they are defined everywhere and not just in the lattice points. And another technical point is extension, because perhaps I could draw a picture. Let's say that you have atomic lattice like this. Then you can see that these two atoms should probably interact because they are their mutual next to nearest neighbors. But in the formalism of cell energies, we need to include some kind of ghost atom, and for that the deformation needs to be extended also beyond the cross section. And as it is common in dimension reduction problems, we change variables to work on a fixed domain. That is called omega. And now, what does this give us when we are in the thin regime where the thickness is much larger than the interatomic distance? we obtain a functional that is an integral of some quadratic expression in torsions and in torsion and curvatures, the ones that I had on a previous slide. So not the ones that you know in a geometry, because this is a mechanical theory. Okay, now I see that there's a typo due to a different LaTeX editor. So obviously this plus infinity should be on another line. This limiting functional can be related to the one that Mora and Müller obtained. These theories are equivalent, except that here the model is still aware of the cubic lattice. So this is the source of anisotropy. But what's more interesting is the ultra-thin scaling, where we obtain again an integral of a quadratic expression, but this time it's an ultra-thin quadratic form that I have on the next slide, and you will see some new terms there. So this gives some novel theory that can be better suited for the description of nanowires. As you saw it on the slide with the Mora-Müller functional, again, this relaxed quadratic form is defined by some auxiliary minimization, but it's a discrete one because there is always a fixed number of atoms in the cross section. This alpha is related to some higher order effects, such as warping the cross section during torsion, or the change of the thickness because of bending, and it's given by a discrete two-dimensional gradient for ultra-thin rods. And there's another new expression that we call the ultra-thin correction, and this would not be obtained by using Cauchy-Born rule to derive continuum theory. And the last thing that is different is this longitudinal stretch that can be shown to be zero in the 3D to 1D continuum case of Mora and Müller. So to recap, we have an ultra-thin correction in the ultra-thin rod model, and also surface energy. If I go back to this cross section, it can, here we have a full cell, but these atoms don't have any real neighbors here. So this gives rise to some surface effects. Here I tried to simulate what the minimizers might be. On the left, you can see the case of bending, and on the right, the case of torsion. So the warping can be seen. And if you want to experiment, the code is available, although I haven't uploaded the most recent version. And now we can get to the fracture modeling. I will first introduce the model and some specific examples, and then I will show you how to prove the gamma convergence result. We need to change modeling assumptions. So this time we consider a sequence of cell energies, or if you want, a sequence of materials that become more and more brittle. And some assumptions are the same as in the elastic case, but there are some new ones. For example, this assumption of technical nature that allows us to construct a recovery sequence for an arbitrary sequence of interatomic distances. And also, if we are away from the discrete set of rotations, these energies are bounded from below, so that so that the fracture is penalized in a way. We don't want the rod to fracture everywhere. And the last assumption is some maximum interaction range. And this covers the case of Leonard-Jones type potentials with a proper scaling of their asymptotics. In the gamma limit, we obtain the elastic part that you have seen in the ultra-thin case, and also another term, which is like some crack energy. It depends on the crack opening, at least in the general case, and also on the different rotations on each side of the crack. So you can model cracks due to torsion. And it covers full cracks and kinks, where the deformation is continuous, but its derivative is not. Since the expression for the crack energy is a bit involved, let's start with some elementary case. So let's take the specific examples of nearest neighbor and next to nearest neighbor interactions with Leonard-Jones potentials that approach some asymptotic value. And then if we have a full crack, so the one-sided limits of the deformation don't match at the crack point, then this fracture energy is given by the number of broken bonds across the cross-section times this asymptotic value. And if we have the case of a kink or a torsional crack, where there's no jump of the deformation itself, then it will be more difficult to derive an analytical expression for the fracture energy, but it can be shown that the energy of a full crack is strictly larger than the fracture energy of a kink. This can be done by comparing the energy, and when you have a full crack, you can always move the other piece of the rod in such a way that there's at least one bond that is intact. This is the general expression for the crack energy. It comes from mapping the neighborhood of a crack onto a fixed interval, and we minimize overall asymptotic energies to produce such a crack. These two lines refer to boundary conditions. So let's say that this is the neighborhood a crack that is blown up to this interval -1,1, then there are some regions near the boundary where these competitors in the auxiliary minimizations need to be affine, but they converge. Of course, the most desirable would be to have some fixed rigid motions, but we weren't able to derive such a cell formula. It can also remind you of homogenization, where such expressions arise. Now I will say some words about the gamma convergence proof. The overall scheme is as usual. We need to prove compactness. Traditionally, this is some condition that together with gamma convergence ensures the convergence of minimizers of the approximate problems to the precise or the effective problem. But here compactness is also needed in the proof of the Limit inequality. In the elastic part of the energy, we need to implement the steps similar to what Frieseke, James, and Müller did for plates. But as you will see, there are some peculiarities due to the fact that we work with 3×8 matrices that have more components. The piecewise, no, rigidity estimate of Frieseke, James, Müller lets us approximate the rod by rigid motions. We need to identify the limiting strain, and then we rely on some Taylor expansion of the cell energy. For the crack part, we use the blow-up method, and we need to derive a cell formula with rigid converging boundary values. Conceptually, this is similar to the result of Friedrich Kreutz and Schmidt on polycrystals, where they also have different kinds of cell formulas. But since they work with different potentials, we cannot use their methods to prove such a comparison of different cell formulas. And in the Lim-sup inequality, we first construct a sequence with localized cracks. And another technical issue is moving back bits that try to fly away to infinity. So now that you've seen the scheme, I will proceed in greater detail. Now let's focus on compactness. So let's say that you have a sequence with a finite bending and torsion energy, and also with an L infinity bound. From this, it follows that the number of broken slices is bounded, because for every crack you pay a certain energy, and in this scaling the number of slices just can't blow up to infinity. And when I'm talking about broken slices, it's important to also say what I mean by this. So in our case, it's convenient to work with the distance of the discrete gradient to this discrete set of rotations, which is a subset of the set of 3×8 matrices. Then, since all the crack points or the projections of broken slices onto the axis of the rod lie in a finite, in a bounded interval, then by simple compactness in the real numbers, they converge. We can assume without loss of generality that there is always the same number of cracks, and also these broken slices are confined to some regions of small measure, and they don't bother us if epsilon is sufficiently small. Then we have some safety distance to broken slices. So on the elastic portions, we can use the compactness theorem of Mora and Müller in the purely continuum setting with only minor modifications. And we obtain a sequence of mappings capital R epsilon that converge to some curve in the set of rotations, and these rescaled gradients of the interpolated deformations converge to the same limit. This rotation curve lies in the space of piecewise H1 mappings, and the convergence is local in L2. And like this, we can also obtain the convergence of integrals of these or primitive functions. And then it is also useful to define an auxiliary sequence of measures, and we have weak star compactness, and then this will be used in the blow-up argument. Then let's move on to the lim-inf inequality. Probably all of you know that in gamma convergence you have two tasks, the lim-inf and the lim-sup inequality. So suppose that we have a convergent sequence of deformations, and the only interesting case is the one with low energy. Otherwise, the lim-inf inequality holds trivially. So we can apply compactness that we saw on the previous slide. And then, in a similar manner as in the work of Frieseke, James, and Müller, we can use frame indifference to derive an expression where we evaluate the energy at the discrete identity plus some remainder, which has the meaning of some nonlinear strain. Perhaps it can remind you of the Biot's stress tensor. And from compactness, we get weak convergence of these quantities. The difficulty now lies in the fact that these are 3×8 matrices. So they have an affine component as in the Mora-Müller paper, but also many more degrees of freedom coming from the displacements of corners of lattice cube. And we need to identify those. In the elastic part of the proof, this is the most difficult point. But it gives you extra information. So it gives these extra displacements alpha that remain discrete in the ultra-thin scaling, and also it gives the ultra-thin correction, which you saw on the slide with the expression for the relaxed quadratic form. Yeah, the proof is done by splitting G epsilon into a transversal and longitudinal component. And after that, it's possible to expand the total energy, that is the cell energy plus the surface energy around the discrete identity, and proceed in a similar way as Frieseke-James-Müller or Morla-Müller. In the Craig part, we can define some auxiliary measure that is simply the trace of the counting measure onto the discontinuity set. And then we have a lower bound by the radon-nicodime derivative of mu that we got from compactness with respect to this Craig measure, and then with a sequence of radii that converge to zero, which give neighborhoods of the Craig point, we finally arrive at some preliminary cell formula. But we need to blow up this neighborhood of a Craig point, and that leads to a cell formula where we can have some non-rigid motions on the boundary, but this is not satisfactory because if we aim at having some model that can be numerically approximated, it's better to have rigid boundary values. And these steps are okay. So these steps are similar to some classical arguments in the book of Ambrosio and Palera about free discontinuity problems. And in the last step, to prove the lim-inf inequality, we estimate the preliminary cell formula psi from below by the final cell formula with rigid boundary values. How can this be done? Let's say that you have the optimal triplet of sequences for the preliminary cell formula. This minimizes over triplets of sequences. Perhaps let me briefly go back. Yeah, here it was. So in fact, this minimum is taken over sequences of interatomic distances, Craig deformations, and some neighborhoods of the Craig. This is also the case for psi. I spare you the definition of psi, but you can imagine something equally horrible, something equally nice. And the goal is to find some Vn that is admissible as a competitor in the final cell formula, but the energy shouldn't increase. So due to symmetry, it's enough to restrict ourselves to the left neighborhood of the Craig. And then it is a bit technical, but it can be shown that there is at least one favorable rod slice where we can take the Craig part up to now and then continue in a rigid way. It's possible to apply again the geometric rigidity theorem of Frieseke-James-Müller. Yeah, so this is what I just said. So with this, we can move on to the lim-sup inequality. An essential part is localization of the crack. This is a lemma that may be of some independent interest, and it says that it's possible to confine fracture to a fixed number of rod slices. So for any error epsilon, there exists a fixed number of slices and some sequences of interatomic distances and radii around the crack, and some modified deformations that are shown in this third picture, that are piecewise affine on the lattice, such that the limb sub of energy contained in this blown up crack neighborhood -1, satisfy this estimate. So basically the energy is not much worse. And this is done in 3 steps. It's the most technical part of the whole work, but basically we first rigidify some portions of these yn that we would obtain as optimal sequences for the self formula, and then we just telescopically shift them so that there is only a small number of cracked slices. And now, what is this good for? Well, in the definition of gamma convergence, we need some recovery sequence for any sequence of interatomic distances, not just the one that we get from considering a minimizer in the cell formula. So the technical step is to localize cracks first by the lemma that you saw on the previous slide, and then transfer the deformation to a compatible lattice, that is a lattice Then another technical point that you always encounter when you try to do dimension reduction in fracture problems is parts of your specimen escaping to infinity. People solve it in different ways. Either they confine everything to a large box with the diameter being the diameter of universe, for instance, which gives you a nice infinity bound, or you can work with some generalized functions of generalized special functions of bounded variation. In our case, with the maximum interaction range property, it's possible to shift the escaping pieces back. So the Leonard-Jones potentials can have some asymptotics. They don't need to be cut off roughly, but still we need to be able to modify the deformations in such a way that the energy is not destroyed. And then we put everything together. So without loss of generality, we can assume that the deformation for which we want a recovery sequence and these director fields are smooth and rigid near cracks, because otherwise density argument can be used. In elastic parts, we have some canonical choice of a recovery sequence where you have the deformation of the mid fiber of the rod, then linear displacements along the directors, something that approximates the longitudinal stretch, and something that gives you the warping. And we update this by this crack sequence from the cell formula near crack points. So to summarize, we derived models for the bending, torsion, and brittle fracture of ultra-thin rods motivated by the modeling of nanowires. Our model features surface contributions and ultra-thin correction terms that can be useful for nanowires containing only a few atoms in the perpendicular direction. Different modes of fracture can be described, even folds or torsion of cracks, and then a lot could be still done, like some numerical implementation or different crystallographic lattices, even though this quickly gets very technical, or heterogeneous nanostructures. And the case of plates is obviously more difficult because you would have different crack patterns, and probably you wouldn't escape the obstacle of needing some quantitative piecewise rigidity estimate in SBV. And another interesting problem would be the convergence of equilibria that is not just global minimizers. So thank you very much for coming, and if you have any questions or remarks, I'll be happy to hear.